My name is Benjamin Richards, and this is my project report for Mech 120 Pneumatics and Hydraulics. For this project, I had to create a pneumatic system capable of climbing a ladder. There were a few main requirements for the system. 1. The robot could not begin climbing the ladder higher than the 4th rung. 2. The base of the robot could not be used to hold onto the ladder, meaning the robot would have to be actively holding onto the ladder. If the grabbing mechanism were to be removed from the rung, it should fall down. 3. The robot had to touch each rung of the ladder on the way up. And 4. This action should all be automated, stopping at the last rung. I opted for a more complex design, in which my robot scales the ladder in a fashion mimicking how a person would climb a ladder. As such, my robot required 4 actuators, 2 of which control the position of the climbing arms, and the other 2 are used to climb up. There were only 2 real issues during the build phase. One was creating a mounting point for the vertical actuators, which required that I cut away some of the metal to allow the actuator the ability to pivot freely, and the other was finding a way to attach the positioning actuators to the climbing arms in a way that allowed all components to move without resistance. The solution to this problem was creating a set of custom shaft collars using SolidWorks, and a dowel that attached to the end of the positioning actuators. These work together to let the positioning actuators move as freely as possible and dynamically move up and down the lifting actuator as necessary. The print material offered a surprising amount of strength, as on one occasion a positioning actuator retracted while still gripping the rung, and the dowel was able to pull itself free of the collar rather than snapping. With these problems taken care of, my pneumatic system ended up consisting of 4 double-acting cylinders, 4 5 two-way DCVs, and 8 flow control valves, all fed from a manifold connected to the regulator. 4 reach sensors were used to monitor the position of the actuators by using them as inputs into the Festo EasyPort, which used all 8 of its outputs to control the directional control valves. I also used 3 additional inputs for user control, consisting of a start, stop, and reset button. FluidSim was used for the logic needed to control such a complex system, and once the start button is pressed, the system will climb all the way to the top rung and stop. Now that I have described the system, here is a clip of it in action. Following this initial run, I reduced some friction caused by the rear support bar by wedging paper between the ladder and the bar, which smoothed the climbing action considerably. I also increased the flow rate of the climbing arms, making the climb cycle both shorter and smoother. Finally, I changed the position of the hands so the robot no longer grabbed itself on the way up. Here you can see the result of these changes, alongside the ladder logic at work in FluidSim. As can be seen, about 4 seconds were reduced from the climb time. Now, this is not the most efficient design for such a robot, and if I were to make a new one with the intention of the shortest time, I would reduce the number of actuators and change the climbing mechanism to require only 1 climbing arm, and some form of fast-acting latch to prevent the robot from falling down. As is, I enjoyed the challenge this project presented, and am very pleased with the end result.